Hi, Wheaton Earth Geology students. Today we're going to start off with the formation of the Earth, which is our first notes of the year. How exciting. All right, so before we get started with the formation of the Earth, let's talk about Uniformitarianism. And you can sum that up by just saying that the present is the key to the past. Now, to kind of flesh that out, what that's really talking about is, no one was around 300 million years ago to write this stuff down or to take rock samples. So how do we know this stuff from the past? And it's based on this idea that the processes that are happening on Earth now were the same processes that were happening 300 million years ago or 1 billion years ago. Okay, water flows now the same way it flowed back then. Magma forms the same way now as it formed back then. Okay, so from that we can kind of draw conclusions, and this is really the fundamental concept in geology, so we can figure this stuff out. Okay, so basalt is a perfect example. So magma in Hawaii flows out and it's very runny and it cools off and it forms basalt with a specific chemical composition. Okay, so if we can find this basalt from 300 million years ago, okay, we're going to say that it forms the same way as it forms now. Okay, and that's basically what Uniformitarianism is talking about. All right, so if we go to the formation of the universe, you guys probably heard of this stuff before. We're not going to spend a ton of time on it because this is covered in astronomy, but that's the Big Bang Theory, right? So that's the beginning of everything, and that was about 13.8 billion years ago. How do we know that? There's all kinds of stuff that we could dive into, but again, this more astronomy class, we've got this background radiation that we look at. For us, it's important because we want to look at, ultimately, the relationship of when the universe formed compared to when the Earth formed, or our solar system formed. Okay, so that's what we're going to kind of look at here in a little bit. So this is just a picture showing that concept of the Big Bang. We don't know what's back before here, and then the universe has expanded ever since. Okay, so our solar system started off as a gas nebula about 5 billion years ago. So again, if you did the math there, right, it's about, not quite, but almost 10 billion years had gone by before our sun was even around. Okay, so but we started off as this gas nebula, which was just homogeneous mix of gases out there in space. Now, homogeneous, if you don't remember homogeneous means it's uniform throughout. Okay, so it was just kind of consistent. But then what started to happen is the gases started to come together, accrete and condensate because of gravity, right? And then a little protostar started to form. So we didn't have a star yet, but all the stuff started to kind of coalesce together. The dust started to spin around in a big circle because of that gravity. Okay, and then eventually our nuclear fusion started on our star, and this is how all stars work. And then it started to heat up. Now all this other junk out here, which is basically you and me, what we're made out of, all those atoms and stuff, started to just kind of coalesce together. But it was very uniform. So all of this material kind of mixed together, and it was all hot, right? And because it was very, a lot of particle movement going on, and it was uniform, so it was hot throughout, and that's kind of a key idea. It's homogeneous because of that temperature. So again, about 4.6 billion years ago is when our planet Earth, what we call home, finally started to form. And at this point, we were only about 200 minerals. Okay, so it started to all kind of coalesce together, and again, at this point, we're still really hot and uniform. Think about it, just a big ball of magma or lava floating out in space. Okay, so not very many minerals, but they started to form because of these chemical reactions and the melting and the, all kinds of other good chemistry stuff going on. All right, then what started to happen, though, was this process of differentiation. Now, what differentiation is the idea of, or just like the word kind of different is hidden in there, is that the Earth started to cool, right? And as it started to cool, the more dense stuff sank down towards the middle, the less dense stuff came up towards the top. Okay, so we had to start to have this difference in temperature across the different layers. You can see down here on the bottom, as we started to cool off, we started to get these different layers. Okay, now there was heat still on the inside of the Earth, okay, and that heat was still generated through 3 processes, okay, because the inside of the Earth is still hot now. One of the processes is due to gravity, right, and pressure. Now these things ultimately led to that differentiation. So we have on Earth right now a cool outer surface, right? The crust is all rocky and frozen, but the inside of the Earth is still very, very hot, right? So one of the causes of that heat was this gravity that led to pressure, right? And that generates heat. So the inside of the Earth is really hot in part because of all that pressure. So we call that gravitational collapse. Okay. Another cause of that is radioactive decay. Okay, radioactive decay. So we've got all this radioactive material, uraniums and plutoniums and all that stuff in there, and that stuff is, as those atoms are decomposing, right, and breaking down, they're generating lots of atomic heat and energy. Okay, so that's another cause. And the last one that, and this is kind of a remnant, we don't have it really happening now on the great scale, but when the solar system was forming, we were getting pounded by all kinds of comets and asteroids and planetesimals, okay, like this, and that created a lot of heat. Now, we were about, around the time of the Earth formation, shortly after, we got struck by something huge, a little mini planet, and that's what this animation is showing here. And what that has led scientists to do is, this is why we have our moon. Okay, so we got struck by something large, way, way, way back, way before there was life or anything. And that led to the formation. But that left kind of this heat behind. So that's some processes how we got it. Now, again, just some kind of side note here, evidence of how we know that this happens. This happened a lot in our early solar system because there was a lot going on. Right now it's kind of boring out there. It's a lot of just kind of space. But early on we had all kinds of stuff going on. So Mercury has a real thin mantle and crust. Venus spins the opposite direction, implying it maybe, or we were struck by an object. Okay, Mars bulges out on a side, which is evidence of it being struck by something. Uranus spins on its side. Okay, so it doesn't spin this way; it spins that way. So again, this is all evidence that we were struck by something large early on. Okay, now what does this all mean? Differentiation. Why is this so important? Well, the fact that the Earth kind of differentiated, we had this hot, dense center and the cooler, less dense outside, led to the formation of the crust of the Earth. And that's pretty important to us, right? Because we need something to walk on, right? And then the second thing is going to be the formation of the atmosphere, which I'll talk about here in a second. All right, so 4.4 billion years is now where we're at. So now we've got the surfaces solidified, okay? And because, again, all this melting and reactions, we're up to about 1,500 different minerals. Now, again, you don't really maybe know what minerals are yet, but we'll talk more about that as we go here. But this was black Earth, okay? And basically, think of it, this was a nasty place, okay? Just black, hot rock, comets, asteroids flying down on us, lava everywhere. Wasn't real nice place, okay? But we get that formation of what we see now with our different layers of the interior of the Earth, and ultimately the crust, which is, again, important for us. Okay, and we believe that inside of the Earth is primarily iron and nickel. And we'll talk about that stuff a little bit later this semester. So our first atmosphere was hydrogen and heliums, but we lost that, okay, because the sun, as the sun was growing up, right, it was getting a little bit stronger and it was blasting out all the solar wind. All that hydrogen and helium, because it has such low atomic weights or atomic masses, got blasted off the surface of the Earth, and that got all pushed out to the outer portions of the solar system, and that's where we see it now with our gas giants, right? These are all gas planets because they're further away from the sun, okay, as well as comets out there. But, again, the fact that we had this dense, because of differentiation, we had this dense core on the inside, and it was made out of iron and nickel, and it's spinning around. It created a magnetic field, okay, and that magnetic field acts kind of like a force field and protects us, okay, and we'll come back to that in a little bit. Now, meanwhile, while that was happening, okay, our magnetic field was kind of protecting us from those solar winds, volcanoes were belching out all of this stuff onto Earth's surface, okay, and this is when we get, hooray, water, okay, once that moves out of the way, you'll be able to see down there about 3.5 billion years ago, so about 1 billion years after the Earth formed, we start to get water collecting on the surface, okay. And that was obviously very important because life, yeah. So without that water, we're not going to have any life. So life formed, okay, which is kind of interesting. And we'll get to that a little bit more. Because that early atmosphere did not have oxygen, okay. It was all kinds of really gross stuff like ammonia and carbon dioxide. But guess what? These little critters that were in the ocean, they love that stuff. They eat it up. And guess what they produce? Remember biology? Oh yeah, oxygen, right? The oxygen over here. So that was very important to us. Now, about 2 billion years ago then, oxygen starts to accumulate in our atmosphere, right? So it starts to build up. And what that started to do, it started to rust everything, okay? So we see what, at this point, scientists call red Earth. It's this layer on Earth where all of a sudden all of the stuff that had iron in it, all these rocks and whatever, started to rust because they started to get oxidized with the oxygen that's in the atmosphere. So we can see that layer on Earth when that really occurs. But again, as this happens, the addition of all that oxygen really let our minerals start to explode even more. We got up to 2,500 minerals at this point, so we're adding more and more. All right, so we'll fast forward even further. 700 million years ago, this is just kind of a little side note here, but we had a portion of time on Earth where it was snowball Earth, where scientists believe that most of the Earth was glaciated and covered with ice and snow, and we'll learn about that a little bit later. And then ultimately, 400 million years ago, we then get multicellular organisms showing up, which is green Earth. Okay, and again, minerals diversifying at all times as we go. Ultimately, to the point where we get up to about 3,800 minerals, 3,800 minerals, and that's about where we are now. Okay, so again, that's a very fast history of the Earth. If you guys have any questions, or anytime you watch these videos, if you're not sure, just pause, rewind, watch them again, and of course, I'm available for you to ask questions in class. Have a good day.